we're going to use a use case, of course, and the way it's going to be split is that first I'll start with presenting something, how we would proceed, how to start to build a pipeline, and then I prepared a Google Colab notebook for you, which I'll ask you to fill in, and me and Pedro and Hakim will go around and try to help, so you can actually learn how to do something and basically follow me. I'm going to be explaining something and you're going to be implementing them for a few minutes. Then I'm going to come back to explaining, and then you're going to implement, and we're going to move that way in iterative fashion, so to speak. So what we're going to try to do is that we're going to first thing that you always need to do in a data science project, if you start from scratch, is you want to define quantifiable metrics for which you try to optimize. For example, if you're trying to predict something, you're going to find a metric that will quantify in an easy and objective way whether your prediction is good or bad. Once you have that, you're going to take your data set and you're going to do some exploration, see what kind of features are there, whether you need to do some serious feature engineering, whether you can just try it as it is, stuff like that. You're going to plot a lot of stuff, visualize a lot of stuff. Then you need to process it to make the machine learning ready. So if you have data that is non-numerical, so for example, strings, that's something in general you need to have to deal with in one way or another. You need to make sure that you deal somehow with missing values, etc. Then what we're going to do is we're going to train a very simple model and just report the findings, see if it's good or not. And in the end, I'm going to just tell you what you would do further on if we had more time. So these are the things that we're going to do, but in every machine learning project or every data science project, there are also many more things kind of outside of normal modeling. So sometimes you need to talk with the client and actually redefine the scope of the project, because it might be a bit too ambitious, or maybe he doesn't actually know what he wants to do, but you can tell him that. You can discuss other data sources. Maybe there are some things that you know that would really help, but are not included in the data set as of this. We're not going to do in-depth feature engineering, which is oftentimes very useful and really improves the quality because of time constraints. And we're not going to experiment with a range of machine learning methods. We're just going to try one or two just to give you a taste. But normally you would try different ones, see what works, what doesn't. And of course, we won't put it into production, which is normally the last step of a data science project. So the problem that we have on hand right now is we're trying to predict using a data set about the loans, and we're going to have information about the loans themselves and the people that take the loans. We're trying to predict which customers won't pay back the loans on time. So which are going to be late, which are going to be on time. This is, as you can guess, a binary classification. We're just going to, our target variable, so the thing that we try to predict, is just going to be whether it's on time or if it's late. Normally, we would discuss with the business side which type of error is more important, whether it's more important to predict someone that would be late but is actually on time, or the other way around. In most cases, it's actually not equally important. Sometimes you really want to catch everyone that's going to be late or commits fraud. Sometimes it doesn't really matter. What we're going to deal with is probably a very unbalanced data set. We can probably guess that most people would pay the loans on time. And if you have unbalanced data sets, then you need to take it into account when you do modeling, when you do pre-processing. So that's sort of an overview of what we're going to deal with. And I'm going to start with the first point. So how do we define a quantifiable metric? The best way to do that for binary classification specifically is start with confusion metrics. Confusion metrics is something that you can see right here. So basically, create a very small 2x2 matrix with predicted value and actual value, so the real one. And what you're gonna there have is the negative values that were predicted as negative, positive values that were predicted as positive, and etc. to remaining ones. And out of those, these are 4 different numbers, but in general, you want to optimize for one particular number. So we need to try to find a way to summarize this matrix into just one number. And there's a number of ways to do that. Some of them are better, some of them are worse. So I'll just discuss a few. First of all, you have something that's called accuracy. So basically, you just sum the true positives and true negatives. So here, where the algorithm was right, and you divide by everything. But this has a range of problems because, let me now go to the next slide. See here, you have very unbalanced data set, and basically almost everything is false. No problem. And only very few actual labels are true. So if you look at this confusion matrix, it doesn't look too good. You are more often wrong than right when you try to predict whether something is positive or not. But if you try to compute accuracy here, it's more than 0.9. So it seems to be very high. But actually, it's almost random prediction. And you seem to have a very good result. So in general, that accuracy is not a very good metric and should not be used.
Excuse me.
Sure.
Sorry, I missed you there. Can you please go back and
okay.
Tell us in what respect you're saying like false true, in what respect, what are these, what assumptions are there, and what is 180, what is 70?
So yeah,
take an example.
It's basically what you have here. Yeah. So you have predicted positive. So in this cell here, what we're gonna have is it's predicted to be true, and it's actually true. There are only 3 of those. Okay. It's predicted to be true, but it's actually false. 7 of those. And it's predicted to be false, but it's actually true. So when it comes to positive class only, so these 2, the algorithm is way more often wrong than right. You see it now?
Maybe later on we can talk about
okay, yeah, let's do that. But basically, if you have very unbalanced data set, as I said, this will dominate almost everything because you can just predict majority class all the time. And if you predict majority class, majority of your examples are going to be labeled correctly, and you're going to have a very good accuracy score. So it's not the very best way to create a metric. There are other ways. Namely recall and precision. Recall is true positive. So this is the number of things in this cell divided by number of things of this cell, true positive, plus the number of false negatives. So we're basically just thinking about the positive class here. And recall is basically, again, this divided by this column. So we're thinking about how good it is with their positive predictions. And recall is how good is the algorithm with actual predictions, or like actual numbers. So these 2 things paint a different picture. Here you can see that precision and recall is not that high. It's not nearly as high as the accuracy. So we have now 2 numbers which paint a better, more accurate picture and give more reasonable results. But we still want to try to sort of condense that into one number. And for that, there's something that people call F-scores. And the most simple example is that if you assume that the precision and recall is equally important, we have something that's called F1 score. F1 score is basically a harmonic mean between a precision and a recall. So it weights them equally and then creates a mean. Harmonic mean is always lower than normal arithmetic mean. So again, it gives a result that is only really good if your algorithm actually performs well. And that's something we're gonna use. Yeah, it's a good practice to use F1 if you have no clue what you're gonna do. And now, once we define that, a few words about the whole pipeline of data science projects. So you start with data cleaning once you have the data. Then you do some data exploration, so visualization, you're trying to see what needs to be done. Then you do whatever needs to be done. And sometimes you need to go back because you need to transform a certain feature. And then out of this, you have a new feature and you want to plot that, see how it looks. So it's an iterative process, and when that's more or less done, you go into modeling and you normally go back to data exploration and data processing again once you have a first proof of concept. So the first task that you'll actually start doing something is data cleaning. Here I divided that into 2 columns. First, it's sort of like thinking. So you're gonna take a look at the data, determine what the data types are for all columns. It's very easy. And then you'll have to one hot encode some variables you just remove, some variables you try to rank. Second thing is you'll try to identify the columns that are completely irrelevant. Some of the columns that you have in your data set is, let's say, customer ID. Customer ID has no predictive power for sure, and you can just remove that. It might be loan ID. It might be some other things that you probably predict that won't be relevant, like the state. Might in the end turn out to be relevant, but the first proof of concept, you're better off just removing them. And you have to determine how to handle missing data. If you have a lot of missing data in a given column, it's probably best to remove the column. If you have a lot of missing data in certain rows, it's better to remove rows and not columns. You can also use a mixed schemes, or you try to do some data imputation. So if you're dealing with time series, for example, you might want to impute in the missing cell, say a median or a mean between the values beforehand and after that. Or you can do some more advanced statistical techniques when you basically create a spline, and in that way you fill in missing values. So this is time when we actually stop, and everyone that has a laptop, please open one of the Google Colabs, which is called scaffolding, IPNB. And all the others, I'd like you to join with the people that have laptops, so you can still do something. Okay, so you probably all loaded the file, and now most of you should have solved the issue of how to remove the missing points. So that's just an example of how you can do that. I mean, you need to know a bit of pandas, but I'll try to explain step by step. So what you select here is you select, we'll go from the inside out. We're gonna look at the missingness ratio, which is something that I computed above it. Looking here, which is basically is you go and find, this is nice function is null, which computes true for every not a number in the data frame and false for everything else. So basically this just gives you a data frame, which just in every cell, it's either true or false. If it's missing, it's true, otherwise it's false. And we're gonna use that to remove all these missing values. So if missingness ratio, so for every column, if this ratio, so ratio to true to false is smaller than 0.2, so it's almost everything is missing, we take all of these columns. We find the index of that in the data frame, and we just drop everything there. And this creates data frame of where everything that is missing is removed. So that's how we deal with cleaning. And now to move forward, we want to remove some columns that are not important. So first of all, for loan status, for the target variable that we have, there are 5 different, as you can see over there. We want to just focus on the things that are late. So if it's still ongoing loan, current, or if final payment is in progress but it's not done, it's still ongoing. So we're just gonna remove from the data frame everything that's either current or final payment in progress. And then we're gonna explore the data. So we look at our target variable, which is loan status. And as you can see, most of them are completed, so they were not late. Some of them were very late, which means defaulted, and then past due number of days, and charged off. Charged off is basically defaulted, but not formally defaulted. To create our target variable, which needs to be either 0 or 1 and not 5 different values as we have here, we're gonna say that the target variable is true if df that we have is completed. If it's not equal to completed, it's going to be false. So that's how you create just a binary variable target. And of course, in order, we cannot keep the launch status in the data frame because it would be used as a feature, and it would perfectly predict the target because it was used to create the target. So we need to drop that from the data frame. So that would be the second stage. And now we're gonna work on making sure that you can actually feed all the data into an algorithm. So I'm just printing out all the data types that you have in all the columns, just to have a quick look. And if you have an object, that means it might be a string, it might be something very strange, but it's definitely not a number. Integers, floats, and booleans are number or can be treated as numbers. Booleans can be treated as numbers. So we know that we have some columns that we cannot just plug into the machine learning model. We need to do something with them. So what I'm going to do, I'm going to split that into good types, so the things that we don't have to work with. So we're going to select data types, and we're going to exclude everything that is an object. And we're going to look at bad types, so the things that we cannot directly work with. And we're just going to include everything that's an object. And now let's take a look at these bad types that we have. So just bad types head. Head is a very nice method that just prints every first 10 or 5 rows. And you can also input a number there. It's going to print first n rows of a data frame. And here you can take a look, what are these bad things. So listing key, just ID. Lots of datetime values. We have datetime value here. You have datetime value here. You have datetime value here. So lots of datetimes. We don't really have time to deal with datetimes, so we just remove them. They might be relevant because if you took a loan in 2007 and then the crisis came in 2008, you're more likely to have defaulted. But that's not that easy to use in online prediction later on, so we're just removing that right now. One important thing is that here you have income range, which looks like just a categorical variable, but the thing is, it's that it is ordered. You can clearly see that if you make between 25 and 49, and if you make 1000 plus, this is ordered. It's not just things that are completely different. So we'll have to deal with that in a slightly different way than just one-hot encoding everything. So what I first do is I just drop everything that's either an ID. So loan key, everything that has key in it is just an ID. It won't be used at all. And we're gonna drop everything that has a date time in it because it's really hard to work with it later on and we don't have time for that. And yeah, after cleaning, these are the things that we still want to include in our data set because they might be potentially relevant and informational or have predictive power. So we need to start plotting now. And this is kind of thing that just helps us. This is metadata regarding the plotting values. So in order to make them bigger, normally these plots have some default values that will make them smaller and kind of hard to read. That's something you can just copy paste from Google that will make it big enough and nice enough. These are just hard-coded values. And now we're gonna use Seaborn, which is a very nice library that allows you to have really nice colors there to plot every of these interesting features or potentially interesting features. So we're gonna start with borrower states. So from which states they are. And as you can see here, yeah, you cannot really see much except that there's 50 states. So it might be problematic if we want to encode them because then we create 50 different features and dealing with 50 additional features might be problematic because then if you have more features, it's harder to make predictions that are easy to generalize. You basically need, in theory at least, the number of data points that you need to achieve good generalization scales exponentially with 2 to the number of features that you have. So in theory, you want to keep the number of features as low as possible, as long as it preserves generality and as long as you have good predictive power. So we might end up just discarding that. If you were doing later on feature engineering, you can see that you could try dividing that into rich and poor states, or southern and northern states, or anything that you might think is relevant, or just pick California because it's very, very frequent, and remove everything else. Things that you might do, but right now we're just gonna remove that later on. But let's first plot everything else. So now we're plotting occupation. So what people do. Again, kind of disappointing because mostly it's other, so not stated or something strange. And again, if we just want to work with that without really changing anything, it's gonna be super hard because you need the one-hot encode again. Instead, you could try to see which of these jobs tend to make good money or not. So for example, if you're a professor, or a doctor, or an attorney, you probably make a lot of money. If you're a nurse's aide, or homemaker, or to be honest, I don't know, student, college junior, yeah, that one, you probably don't make too much money. So you could try to divide that way and work with that. But again, it's at first pass, it's better to just remove that. And now we have something that's finally interesting, employment status. So again, this, if you look at it, data science is kind of about what's reasonable, what's not reasonable. So here you can see that there are some people that work part-time or are not employed, and you can guess that maybe this is very relevant. And if they are not employed, they are most likely to default order loans. If they are employed full-time, they should be good to go. If they are self-employed, there's a big risk. So again, maybe more likely to default. So we're gonna one-hot encode them. So for every of these values, we're just gonna create a separate feature that says whether they are this or not. So it's gonna be a binary feature, full-time employment, which is gonna evaluate to true or false. If it's true, it means that this particular person that took this particular loan is full-time employed. And last, sorry guys, last visualization is income. So as you can see, here there's a range of different income ranges with not displayed and not employed, which is very small. So for now, we're gonna sort of ignore that, although it could be relevant and informative. And as you can see again, this is something that is ordered, so we need to deal with that somehow. And yeah, I'm just gonna look at what is all the possible values of income range, which you have here. There are not too many of those, and we want to rank them basically from lowest income to highest income and create one feature that just tells them how well off this person is or how much income he makes. So to do that, this is, yeah, pandas relevant. If you don't know pandas, it will be probably hard to do that easily. But what we can do is we create a mapper, so a dictionary or a hash map in other languages. When we, for every, as keys, you have current values, so not displayed, not employed, and then all these values. And this maps to an integer. It could also map to any float or something. It doesn't matter too much. And then we take a look at relevant column, income range. And we're gonna call this relevant column and just replace it with this dictionary. This is kind of intuitive. You just call a dictionary and it applies key value transformation to every value of the cell for a given column. So basically what we end up here, by the way, you have this in the Google Drive, so you can just take a look at it anytime, and this solution is yours. And now, after this transformation, this is what you have. So again, the same, but right now it's just one feature that's also there, but right now it's a numerical feature and it's ranked. So that's something you can directly plug in into the machine learning model. And yeah, as I said before, here we're gonna drop these two columns because there's just too many values there. And for employment status, we want to one-hot encode them, and there are two ways to do that. Normally, if you want to do it fast, you can of course do it manually, but why would you? So either you can use pandas get dummies function, which has syntax like this. You take the data frame and you select the columns that you want to one-hot encode, and it returns the whole data frame, excluding this column, but instead of this column, it returns one-hot encoded features for every possible value in this column. Another way is to use scikit-learn one-hot encode from pre-processing, which gives you the same result.
So in that one gives you the order you want? Because you want to have zero income. It's
no, here we are one-hot encoding employment status, which is not ranked in any way.
Okay, this is not the ranking part.
Yeah, so the ranking part was before that, right?
Okay.
Yeah, and just to see whether it works, I'm gonna print all the columns of the data frame. And as you see in this bed types, we have income range, which is now a ranked feature, and all possible values of employment status. So employment status underscore employed, not employed, part-time, etc. And now that bed types are no longer bed types, they're all numerical, we can concatenate them back with good types. And this is what I do in this line. So I call the function pandas concatenate. And first argument is just all the data frames that I want to concatenate along the axis one. Axis one is columns. I should probably use here columns. Alternative is just you can write here columns instead of one. To make sure that there are no problems with indexes, because they might be different, they might have shifted a bit or something, it's always better to just reset the index and then drop it. And that's how the head of the prepared data looks like. So in the income range, you have numbers, as you should have. In the employment status, you just have 1 or 0 or true and false. In Python, it basically maps to each other. And then all the good things are just the way they were. So here you have all the numerical values that we didn't touch yet. And there is slight, you might, just looking at it, you might think that, say, investment from friends is just always 0. If it's always 0, then why would you keep it? It's not informative for sure. So that's another thing that we want to do. We want to remove all the columns which don't change. If there's only one value there, there's no reason it can help us anyway. Again, there is a number of ways to do that. The way I did it here is that we call whole data frame, and we find the location for which the variance of a column is different than 0. If you have more than one feature, one value in a column, then you'll have variance that's bigger than 0. The only way to have variance that's equal to 0 if everything is constant. So that's a way to filter it out. Maybe in the next version of pandas, they will do something that will just allow you to remove constant columns, but right now you need to do something like that. I was curious whether this actually removed anything. So I just printed the length of all the columns in prepared data, so the data before, and fully prepared data, so the data that we have now. And it turns out that it didn't remove anything. Still good to something that you still can do to make sure that you're not including anything that doesn't change. And now, just to make sure that we didn't introduce any not a number values, I'm gonna drop not a number and see if it dropped anything, but no, everything is fine. So that's basically initial data cleaning and data preparation. Now I'm gonna come back to the slides and talk a bit more about what we're gonna do next. Okay. So yeah, some of these things we already did, luckily. So we're gonna do the data exploration and pre-processing. Let's again map sort of one-to-one. We need to first find out whether the target variable is explicitly in the data set. So in our case, it wasn't. sometimes you might just have, if you deal with a regression problem, you just might have a number, but you need to predict this number. It's already there, you don't need to do anything with that. Sometimes you need to construct it somehow, like we just did. Then we might want to look into pairwise correlation between features. If there are some features that are very strongly correlated with each other, like for example, you might, if you analyze, give an example from manufacturing, if you analyze a wind turbine data, you're gonna have lots of sensors and you're gonna have different sensors for each of the blades. So for example, blade velocity. But the blade velocity of one blade is gonna be exactly the same as the other. If it's not, then it means that probably everything is collapsing. So if you see something that's very strongly correlated with each other, you can just drop one of these features because it's basically the same thing, but it increases the number of dimensions that we have, which is something, as you know, that's bad. Also, we want to, if possible, ensure that the features are independent because lots of machine learning algorithms work based on the assumption that the features are independent. They also, in practice, work if they are not independent, but if we can achieve feature independence, we'd like that. And again, if we have less dimensions, we might have better generalization. Not always, but good rule of thumb. And then, once we've done that, we want to look into correlation between features and the target variable. This is the first and most easy way to see which of the features might be relevant. There might be correlation between them that makes it a bit spurious. So again, if you have two features that are very similar, they will all be predictive of a target variable, but you don't need both of those. So it doesn't give you a really good overview, but it tells you something. And then once we've done that, actually, before that, we need to scale the data before we do correlation, unless you're using pandas, because pandas does it for you internally. So that's what I'm gonna do now. And again, short break for you so you can take a look at the examples, ask me questions, and try to do something. So I guess you've been working on implementing these things, and I'm just gonna walk you through the way I did it here. So the first thing I did after dropping NA to make sure that nothing strange happened is I created a pairwise correlation matrix here, fully prepared data. So the data that we're having right now, .core, again, pandas is magic. You just write .core and it creates fully, it rescales internally and it creates a matrix of correlations. And this is gonna be a huge matrix, and what we're currently interested in is just looking whether something is correlated with our target variable. So I'm just gonna create a new variable that's called correlations target, and I'm gonna look at the correlations regarding target. I'm gonna take the absolute value because I want to sort them and see which of the correlations are the strongest ones. I don't care too much whether it's positive or negative right now. And that's what it outputs. So basically, what you see here is target is obviously correlated with target, but there are some other things that are surprisingly highly correlated with target. And here you see something that's actually something that's called information leak. So it turns out that there are some features here that you would normally have no access to. So if you want to predict whether someone is late with the loans, and it's not late now, but might be in the future, then of course you won't know what is the number of current days that he's late with the payment. And it was in the data set, but we cannot take that into account when we're building our model because that won't be available for us when we do predictions. So this thing, something we need to remove. And then everything with LP, I found out that's also something that we wouldn't have access to in general because this is, again, loan payment. So loan is already being paid back or has already been paid back. And here you have, for example, gross principal loss. So how much money the bank lost on the loan. That's something you don't know before the loan is paid back or not paid back or defaulted. So again, all these things we need to remove. in order to make sure that we don't have any information leak and that our the model that we train will actually predict something on the data that we have available. So we'll have to remove this first 5 features and that one as well. And then interesting thing starts. So we have borrow rate, lender yield, borrower APR, I don't know what it is.
Annual percentage rate.
Exactly. So all these things are strongly, not strongly, but relevantly correlated with our target variable. So these things might have some predictive power when we try to predict whether a person is going to be late on the loans or not. Yes?
How do you decide if 0.22 is interesting, or why is this correlation number? When is the cutoff point where you decide or feel like?
That's a very good question. There is no cutoff point.
That's
what we generally do is you just look at the things that are the highest.
Okay.
And take those into account in the first proof of concept. Later on, you take everything into account, because if you train a deep learning model, it might be that if you take income verifiable in conjunction with something else here, in conjunction with something else here, it suddenly becomes very relevant. Or if you take a logarithm of one of those and the exponent of the other, becomes relevant suddenly. But for now, what you can do, something I didn't do here, is you can plot all of those and look for jumps. If you have something that goes like this and then there is a jump, take everything before the jump, discard everything after the jump. It just do stuff that's reasonable, basically. Okay. There are no hard rules here. If you have something that's like between below 0.5, if you don't do anything with that, it's going to be useless. So you're quite safe discarding all of those in general, not always. So yeah, here I'm going to subjectively choose number of 0.08 because there were like around 10 features there, and 10 features is something that, from experience, is something that you can work with directly. You don't have to do any dimensionality reduction. So yeah, these are the features. I'm just taking this correlations target and printing the index. Index is the name, super easy. And then I'm just choosing these things and making them a list, and then create. This is basically a subset of columns that we're choosing. This is everything that's from here to here, and then we cast it to list. So we have a list of columns that we want to take a subset from. And then we need to, of course, drop all the things that are illegal and wouldn't be available. I hope I dropped them all. And yeah, basically now we know what columns are we're gonna use. So in here is all the columns that we're gonna use in our model. Then the next thing is that I'm taking, again, the correlation matrix, and I want to see how many of these features are correlating within each other. So I'm just gonna look at correlations stronger than 0.5 and sum all of the things that are bigger than 0.5. And what I'm doing here, I'm subtracting the length of the columns, because if you look at this correlation matrix, then every feature is going to be perfectly correlated with each other, with themselves, sorry, not with each other. So we need to subtract the number of columns to remove those obvious correlations. And then we see that there are 10 of those correlations, and because they are symmetric, it's actually 5, because there's 5 here, 5 here. But that means that maybe we should still do some kind of dimensionality reduction to make sure that the features are independent. They don't have to be, but sometimes it's better. But before that, we can actually start modeling. So for modeling, I'm gonna come back to the presentation. And yeah, so to recap, what we're dealing with is a classification problem of unbalanced data. This is something I haven't tackled here. I'm gonna talk about it for later steps. How do we deal with unbalanced data? And we need to remember that we're using F1 score as a metric, because using accuracy with unbalanced data leads to results that don't really show anything and just predict majority class. And the approach that we're gonna take here is you're free to choose one of these two things. You can choose anything else, of course, but they are kind of simple and easy to implement. So first thing, random forest. So you have basically lots of decision trees. What it gives is that you have feature importance, which is, so for each of the trees, you're going on to take the subset of the data and train this tree on the subset. But then you can check what is the performance on the out of bags or on the data that was not used for this particular tree. And if you do that for all the trees that have different features, what you're gonna get is you can approximate how important is the feature, how nicely it improves performance, because you're gonna have some trees with this feature in, some trees with this feature out. So that basically gives feature importance out of the box. In scikit-learn, it's really easy because you can just call .feature importance. And this again is a bit better than just using correlations, because this actually gives you how much it improves if you include this feature. This is of course kind of stochastic, so don't rely on it too much, but if something has really high feature importance, it's most likely to be actually important. This can be used later on with feature engineering. If you want to create a smaller subset, you just take the ones that are very important, or you can use all the features that are in dataset, create random forest, and then only later on do feature selection based on feature importance in the random forest. And then you could try to do that iteratively. And it tends to give good results for binary classification, just from experience. There's nothing more to it. It just tends to work. And another thing is logistic regression. It's basically the simplest classification algorithm you have. And I use it as a benchmark. And basically, if you have something, if you use another technique that has results that are worse than logistic regression, it's a very telling mark that you're overfitting, because logistic regression is really not expressive and it regularizes itself well because it has no expressive power. And for that reason, it very rarely overfits. So if you have something that has more expressive power, like a neural network or an SVM, so it should be able to capture more complexities, but tends to give worse results. This means that you're most likely overfitting and you're modeling noise. So another way to find whether you're overfitting a different algorithm or not. Now I guess I'll just gonna go through the solutions again. So what we start with is we need to separate target and features, obviously. So what we see here is we just take our data frame and select target. And for all the features, we take our data frame and just drop target. As simple as it gets. Then we need to scale our data. Target is scaled. We don't have to scale target, but target is already 0 or 1. So we don't need to do anything with the target as normally. And for the scaler, you have, I think, 5 different scalars that are generally used. You can just take the minimum and maximum and then scale it to 0. You might want to use for some data, which has lots of outliers, something called robust scalar. So basically you do the same thing, but instead of taking min and max, we take the interquartile range 75% and interquartile range 25. And you treat that as 0 and 1 and you scale it. So then the outliers can still be there. But what you want to have is you want to have distribution that is basically mapping 1-to-1 with all the features, or at least it's similar. So you won't have distributions that are very small with very small variance and other distributions that are very big, depending on outliers. So that tends to work better, but here just for illustration purposes, I'm using min-max scalar. And yeah, here we start using scikit-learn for the first time. Scikit-learn is again super easy, just one line of code. You first fit. So we have here this function scalar. You fit, so you basically fit the scalar, find the minimum and maximum of the data, and then you transform the features. So you apply the transformation once you know the parameters of the transformation. And to make it prettier, because if you just did that, you would have a NumPy array, which is something you can work, no problems. But because I want to print it nicely, I'm gonna cast it back to the data frame, and I'm just gonna use the same columns. So once you start doing scikit-learn and you can do modeling, you can still cast back the data frame just to take a look at it. It's not very performant, so in production, of course, you wouldn't do that, but for exploration, it's great. And now you can just see all the features, the head and tail. There's lots of numbers, everything seems to be fine. And now, just to try it out to see if dimensionality reduction can possibly make sense, I'm going to apply PCA, so principal component analysis. What PCA does is it basically finds the directions in the data set. So imagine that your data set has n features. You treat every feature as a separate dimension and try to imagine that you have this hyperspace of all dimensions. And the data is going to be a cloud of points, which in general will have some directions when you have more variance, some directions when you have less variance. What PCA does is it finds the direction of the biggest variance, and it sets that as first principal component. Then, looking at all possible orthogonal dimensions, so you have only 9 of them, it finds another one when you have the biggest variance. And it does that 10 times if you have 10 features, like the last line is trivial because there's only one left. So what it basically does is it aligns the components in the direction when you have the most information. And to make sure it works, you need to always scale the data, because if it's not scaled, you might have one feature which has range from 0 to 10 million, and all the others are from 0 to 5. And then obviously, the PCM algorithm is going to assume that this feature with range from 0 to million has the most information because it has the biggest absolute variance. So always you need to scale your data. Yeah, and then why? So normally you transform a 10-dimensional space to 10-dimensional space, so there is no reduction in features and in dimensions. But what is really nice about it is that because you capture the most information in the first few components, you can discard the later ones, and you still have the most variance of some most information in your data. You don't lose information, but you reduce dimensions. So you basically gain a lot because you reduce dimension, that's something bad, but you lose only smaller percentage of the data. What you do normally is, here you can set that you want to capture all components that have 95% of total variance in the data. Or you can use certain Bayesian techniques that try to guess what is the real dimensionality of the data. Another option. Here, third option, probably the worst, is you just pick a number of components, and let's say 5, and you're gonna take out of these 20 features that I have, I'm gonna take first 5 components. So again, I initialize the PCA transform with the number of components, and then I recast my features into another space which has only 5 dimensions. So here, component features, and I fit and transform the features using PCA, and I just call them component and the number of components. So you're gonna have component 0, so the most important one, component 1, 2, 3, 4. So 5 components in total. So there's a trade-off. You lose information, but you have smaller dimensionality of your data. And the last thing that we're gonna do here is we're gonna just classify our data, trying to see if it can actually predict pretty nicely the whether a person's gonna be late on their loan or not. So we initialize a classifier, which is just a logistic regression. Normally in the brackets here, you have lots of hyperparameters, but just for illustrative purposes, very simple one. And what I'm gonna do here is I'm gonna try to find the real score that you would have on the unseen data. So we're gonna have to stop here and I'll explain what is cross-validation. So normally when you train a data set, you're gonna have a train set when you train the data. And because you train on that, you're gonna overfit at least a bit on the data set, or you should assume so. So you need to have a separate set It's called validation set, where you're gonna check whether your algorithm actually generalizes well or not. And because you choose this randomly, it might be that there is some bias in your choice, and your algorithm is gonna have worse performance than on real random set. So in order to kind of reduce this bias and to make sure that it's as real as possible, we can do that many times, every time choosing, let's say, 80% of the data as your training data, 20% as validation, and we're gonna do that a few times, each time choosing a different subset. And we're gonna always report the score on the validation set. That's basically what is cross-validation. So you create certain number of faults, so this data partitions, you choose all but one as your training set, and the last one, or the other one, is your validation test. And yeah, that's basically what's cross-validation, and it's one of the better ways to try to estimate what's the performance of your algorithm on real unseen data. What you can also do is, apart from that, if you do more things like hyperparameter search, you can also have completely separate test set, which you don't see at all, which algorithm doesn't see at all when it tries to optimize hyperparameters. And then you check the performance of your algorithm on this test set, which also gives you quite good results when it comes to estimating how good a generalization of your algorithm is. So here, I went with just cross-validation route. So what it accepts is initialized classifier, the logistic regression, all the component features that I have. So now I'm trying to see how good the algorithm would work with PCA beforehand, the target variable. Number of faults is set to 5. You normally do 10, but it's faster if you do 5. And the scoring is F1 score. You just put here a string. It can be accuracy. It can be recall, precision, F1, F beta measure, so F1 but weighted with different types of error weighted differently. And then I'm gonna do the same, calculate the same score with normal features. And then what it outputs is a list of scores for each of the faults. So these scores are gonna vary a bit, but I'm just interested in general score. So I take the mean, and I print both the component score, so how good it is if we use principal components, and how good it is if we just use all the features. And as you hopefully see, if you take all the features, it's a bit better here. Also, this score is very, very high, abnormally high. So I guess we didn't remove one of the things that were illegal. So but if you see score that big, you should have an alarm in your head that something might be wrong. It's too good for the first prototype, unless your problem is really easy. But this problem is almost never easy. So anytime you see something that's too good to be true, it is too good to be true. You're not amazing, you just did something wrong. Yeah, and and the last line is sort of the model that we would put to the client. We just take the same classifier and we fit it on full data set with no faults, nothing. We just train it on all the data we have, and then you can just take that and do .predict with new data. Keep in mind that if you have new data, it needs to go through exactly the same pipeline as your training data went through. So you need to remove exactly the same features. You need to scale it exactly the same way. So you need to use exactly the same min-max scaler. If new data has different min and max, you still need to scale it using the alt min and max. Yeah, stuff like that. And if you do PCA, you need to use exactly the same PCA, how do you call this, model as you did for your training data. Now, so basically that's what you would do to create like proof of concept for the client. And now a few closing words and we're done. Yeah, so once this proof of concept is in, client is happy or at least interested, we can start doing more things. We can present other ideas that we'd like to do that next to improve the performance and bring more value to the client. So what we can do on the modeling side, we could change the scoring to something else, and this something else for binary classification can and should most of the times be F beta. F beta is like F1 score, but we weight different types of errors. So false negatives and false positives not equally, but differently. So in this example, I guess that if you want to predict whether someone is late, it's better predicting that someone is late and he's actually on time than predicting that someone is on time and actually is late, because then you lose more money as a bank because he might default or create other charges. We should do proper feature engineering. So again, we need to have some domain expertise or work with people who have domain expertise, and maybe they'll know exactly what kind of things tend to affect whether someone's gonna default or not. If you work in marketing, you would work with salespeople. If you work in banking, you would work with finance people. If you work in manufacturing, you would try to talk to normal engineers, not computer scientists, etc. Right? If you work in medical imaging, you would work with doctors, nurses, stuff like that. And also, just basically, in data science, if you go into new project and you don't know the industry, just read a bit about it so you know what's important there, what are the basics. We can also experiment with more dimensionality reduction methods. So instead of just using PCA, you have different methods. You can do kernel PCA. Kernel PCA is a way to apply PCA, but not in normal hyperspace, but you transform it into a different space that hopefully you make sure that all the correlations are linear. This is something that's kind of borrowed from SVMs, support vector machines, which also use kernels, and kernels are basically a way to cast from one hyperspace to another hyperspace when data is either more linear or more separate, or linearly separate, or has other things that are preferable. We could try out different machine learning algorithms. You could try ensembles of different models. This is something that tends to work really well in Kaggle competitions and things when you really need to achieve cutting-edge performance. If you have models that are heterogeneous and work by different assumptions, different ways, and you create an ensemble of those, all these models have some weak points, but they tend to cancel out, and the whole is more than sum of its parts. You can try deep learning. You can always try deep learning. You can include unlabeled data. So what you do in real problems, almost always just a small subset of data is labeled, and for the rest you have no clue. Here it would be all the loans that are in progress. So you would label the data that is in progress, so basically do prediction of your unlabeled data, and then you retrain. Sometimes it just makes the bias worse of your algorithm. So if there's anything that's doesn't capture the reality, it just gets more pronounced. But sometimes magically it actually starts working better. What you also should do is hyperparameter search. So you have, for all these machine learning algorithms, you have a number of hyperparameters. So almost always you have something that regularizes. For neural networks, you would have number of neurons, you would have dropout rate, you would have number of layers, you would have a solver, you would have step size, all these things. Normally, you just set that to a fixed value. But with grid search, you can retrain the algorithm and do the cross-validation scoring using a number of different hyperparameters and just choose the best one. So that's on the modeling side, so on like more technical data science side, and on less technical data science side, because that also exists, you can try to redefine the problem to better match business requirements. For this case, maybe actually they don't care whether someone is late on the loan or not, but they just care how much they lose money if this person defaults. This is probably the real bottom line of a bank. So you could try to cast this into different light, reformulate it as regression problem when you predict the losses for the bank or the profits for the bank. It matches the business requirements better, but it's probably way harder to do. You can always try to add more data because in most cases, adding more data is just trumps anything you can do to improve the performance of your model. And of course, you need to sooner or later put the model into production, and whether you do it yourself or you work with other people, that really depends on the project. And a bit more closing words for hyperparameter optimization. This is something I really like, so I tend to talk about it a bit too much maybe. You can normally, when you talk about hyperparameter optimization, you optimize the parameters of the model. But the thing is, what impacts the performance of your algorithm is not just the model, but it's the model type. So whether you use SVMs or logistic regression or kernel rich regression or neural networks or decision tree or whatever, this also matters. If you change the dimensionality reduction parameters or type, this will also improve your performance, as you saw here. Using dimensionality reduction is worse than not using it. So always matters. You have different parameters there. You can also optimize that. You can optimize features. That's a big thing. You do feature selection, so you only select a subset of features because some of them will be only noise. They won't matter in the end. So if you don't select that, you don't model noise. So by removing features, you can improve the generalization of your model. And the last thing, you can also change the ways of dealing with missing data. If you do some very smart and fancy way of imputing data, maybe you capture something that was not there, maybe you increase the amount of the data you have that way, and you have a better algorithm. Maybe by doing that, you introduce additional bias in the data set, so it does not portray the reality as good as it would without these imputations. And again, you can also do different types of data imputation or removal. And yeah, you can also overfit those, so you don't always choose the best ones, but that's a bit advanced, so we can skip that. And just remember that you can just really get lost in that, try to squeeze out the last 0.001 of your model, but that doesn't really translate into business profits anymore if you spend too much time on it. That's it. Thank you very much. So yeah, I just kind of suddenly started a consultancy. There were too many projects coming in. So right now we're actively looking for new projects and people, and we're looking mostly for more senior people. And of course, the more projects, the better. So if you know anyone, or if you want to try out something that has to do with data science commercially, or if you have a problem that needs solving, let me know. If you're looking for a job and you're a bit more senior, also let me know.
Okay, any questions?
I have one. So in there you put PCA, which will take components that are linear combinations of the attributes, right?
Yeah.
How do you deal with interpretability of the model? Because you want to deliver something that you can explain to the client.
So in most cases, yes. In some cases, you don't care. You have a black box and they just want to know what is the prediction. So in some cases, you can just do whatever you want, apply very deep learning models that are not interpretable. But in most cases, you're right, of course, you want interpretability. And for that, what you can do is you want to take a look at correlations between features and components. So you're going to have a first component that's correlated with this, this, and that. So you can say that if the prediction of the model takes this concrete feature into account, so for example, in decision tree, it's at the first intersection, you have this particular feature, so this particular component, and this particular component is correlated with that and this feature, then probably these two features matter. You won't have full interpretability, but that's the way to recover it somehow.
Okay.
Yeah.
Yeah, I want to ask something from the business side. So you said you are working in a consultancy.
Yeah.
So how does it work? Like a client comes to you and gives you a data set, clean. How do you like brainstorm? Like how do you decide what outcome to look for?
So first,
how does that work in your
go to the client, or at least that's something we have to do now. And clients don't come to us yet. But basically, you agree to start a project, and there's basically exactly something like that, a proof of concept.
Yeah.
Basically, you need to have your foot in the door. So you create a proof of concept that already provides value, and you agree together. You brainstorm at first what problem they have. Mostly they do know more or less what they want to do. You need to narrow it down. Sometimes you propose another things that they actually like more, and then you do that instead of their initial idea. Then you ask them for data, or again, depending on the use case, they might have some data. It's almost never clean. You can get like 100 CSV files, and for each cell, it's gonna be X equal 5, and this will be one cell.
Yeah.
So you need to pre-process that, and this is most of the work.
And what's the team look like? Like in your team, are you? Is there like do you have like a data engineer and a data scientist working simultaneously?
I wish.
How are you? What's the team setup look like?
So basically, it's me. Hakim helps me a bit, and I have a software engineer that helps a bit with cleaning, productionizing Django things. And that's it. Like, this is really, I'm just getting started right now.
Okay. Are you the founder of this?
Yeah.
Oh, okay.
Yeah.
Beside this, I have a question regarding the presentation.
Sure.
When you say you're doing the filtering, you remove these particular those dimensions.
Yeah.
You filter those, right? And there is this term of collaborative filtering, very popular in the data science community.
That's something completely different.
That's great. Can you relate it?
So it's really unrelated. Here, when I say I filter, I basically just remove stuff based on very simple conditions. So I either just filter out, as in I remove a column, or I filter by saying everything that's, in this case, that is not none stays, everything that is not a number is removed. So that's filtering. Collaborative filtering is basically a way to build a recommender systems when you try to see what things are seen together in case of movies, for example. So something completely different.
Okay, thanks.
Okay. Can you explain a bit about the billboard project that was mentioned? I'm quite curious about that.
Yeah. So I can't say too much because NDAs, especially that it's on camera.
Like that's Philippines.
Okay.
So what I'm doing there is basically we have GPS data, and we try to generalize the population level. What's the exposure of billboards?
Using machine learning?
Yeah, there's machine learning in for
Okay, I can't say too
generalization.
much.
Yeah. Again, like I'm really not sure how much I can say.
Okay.
But that's the general scope
Fair
of the
enough.
project. But it's mostly data processing. Machine learning, almost always in projects, machine learning is going to be like 15%.
Mm-hmm.
If you're lucky, then it's 30.
Do you also have to like write a report at the end explaining all your findings?
Fortunately not.
No?
Not that. I did that once for one project though.
Okay.
But that was oh, yes.
Did you have like another company before this, or this?
No, that was just
So
working.
you're working as
I
a
was working
freelancer.
as a freelancer,
Okay.
and basically now the project exploded. And I have too much work to do, so I need to start hiring people.
Oh, cool.
A technical question about the code.
Yeah.
At the end.
There's a bug.
No. You're talking about PCA and you generate 5 components.
Yes.
There I'm a bit lost. Could be due to lack of understanding it, or but then again you use these 5 components to fit your model, right?
Mm-hmm.
But then I'm lost. Where when you have your fitted model and you want to predict something, or are we inferring something here? What is actually?
So you want to predict?
We don't know which features they are, right? Because
Yes.
now there are
Yes.
components and we
Exactly.
cannot relate anymore to the original data. Is that
So basically that was his question.
I'm sorry.
What we get, what we get here is we want to predict whether a certain feature target being late or nose or not is 0 or 1. And the way we can do that is we can just take the features as they are or we can transform them in some way. If we take features as they are,
Okay.
in most models, you will see what's the import of each particular feature. In decision trees, you will have conditions that split, right?
Yeah.
In random forest, we will have lots of decision trees that do that.
Mm-hmm.
In support vector machines, you're going to have a decision boundary that will be between all these features, etc. And with components, it's going to be exactly the same way, but these components won't be features anymore. Okay. They'll be just numbers, as you said.
Okay.
And then we come to exactly his questions. We can map these features back to components by looking at correlations between the features and these components, because they will obviously be correlated because the components were created from the features.
Okay, thank you.
Okay, anything else? If not, I guess we're done. Thanks a lot again.
Thank you.